Coming to you from the lava fields of Kilauea, we're going to look at random graph evolution. The purpose of this brief screencast is to illustrate the phase transitions that graphs go through when they grow randomly, and also to look at some of the properties of random graphs, and in the process to illustrate some basic operations in igraph in R. So specifically, we're going to illustrate what Barabasi shows in this figure, that as a graph grows randomly with a fixed number of vertices, but you're adding edges, at first, if the average degree of each vertex is less than 1, meaning that you have too few edges to actually touch all the vertices, then there will be no giant component. You're just going to have collections of isolated components. When you hit the critical point, where you have the absolute minimum number of edges needed to connect all the vertices in the graph, so you have an average degree of 1, suddenly a giant component appears, at least a large component that's going to have more vertices in the graph than any other component. Because that's larger, it's more likely to be hit by subsequent additions of edges, and so it grows. And we go into the supercritical phase, where it becomes a giant component, not just the largest component, that encompasses most of the vertices of a graph. There'll be a few isolates. And then when we hit the average degree of each vertex being the log of the number of vertices in the graph, at this point there's a phase transition where the entire graph becomes connected, or perhaps there's only a few isolated nodes with low probability. So we're going to just run a little simulation in igraph that shows these phases. It's not actually going to grow a single graph. We're going to make a new graph for each phase, but it'll show these properties. So let's get to the random growth in action here. Okay, here we are in R. I'm in version 3.3.1. Some of the things I'm going to show you had different names in earlier versions and might change in the future. And I have here a script for what we're going to do. First we'll load library igraph. In this R environment, if you put a cursor on a line and hit command return, it will copy it over to the console and run it. Very convenient. In RStudio, which I recommend that you use, it'll actually advance the cursor to the next line as well, which is very convenient. But I use R because I need to be able to control the window arrangement when making these videos. Okay, so first I'm going to make a window for us to see stuff in Mac OS. We can do this with the quartz command. Windows is going to have a different command. And I'm going to put that up here. And I'm going to tell it to use 2 rows and 2 columns with this parameter command. That way I can plot 4 things in one window. So again, you see it's being copied down here. Now let's look at the content at hand. First of all, we are going to look at the subcritical regime, before the first phase transition, where we have the average degree being less than 1. So there's not enough edges to make a giant component. This means twice the number of edges has to be less than the number of vertices, because each edge has 2 ends. So since I'm going to use 100 vertices, I'm going to choose, I need a number of edges less than 50. I'll choose 25 to make sure that it gives a good clear example. I'm going to use sample GNM, which means the random graphs where we specify the number of vertices n and the number of edges m. So the number of vertices will be 100 and the number of edges will be 25. We could have also used GMP, where we give a probability here instead of a number of edges, and that would have required computing the probability that puts us in this range of k less than 1. I find it more convenient for this demo to just give the number of edges. This was previously called Erdos-Renyi game. You'll see that in the statistical analysis of network data tutorial. And we're going to just assign this to a variable name that's just an arbitrary name that I've constructed to remind myself what it is. Okay, so let's run it there. And now we're going to plot that graph without drawing any vertex labels, give it a small vertex size, and give it a title. And there goes our plot, and we can see that, as expected, there's no giant component. All the clusters are very small. Actually, this is very unusual to see a loop in one of these things. I've run this demo maybe a dozen times in the last few days and never seen a loop. But it can happen with small probability. Now we're going to reach a critical point where the average degree is 1. So we've got just enough edges to touch everybody. This will happen when the number of edges is half the number of vertices. So we're going to do it with 50 edges since we have 100 vertices. And we should see the beginnings of a giant component here. So let's plot that. At first it won't be so giant, but there will be one clear component, here it is, that is starting to grow larger than the others. Where this happens is purely random. Now if we continue to adding edges to this graph, of course this is more likely to be hit by random addition of edges because it has more vertices. If you pick 2 vertices at random, it's more likely to be that one of them will be in this component than in the other component. So that makes it's a winner-take-all or kind of growth, and that makes it grow into the giant component that we're going to see when we get into this supercritical regime. So as we go beyond the average degree being 1, but still below the log of the number of vertices, we're going to go to, see, the log of the number of vertices we have here is, this is the natural log, is 4.605. So I'm going to pick k as 2, so we're clearly in the supercritical regime, but not too close to either boundaries. And I can get that by setting the number of edges to 100, so that there's 200 ends available for the 100 vertices. So let's run that. And let's plot it. Okay. And here we see the giant component. There's one component that's clearly taking over the graph. Okay, finally we're going to go in the connected regime. This is when the average degree is later than the log of the number of vertices. Actually I have n here, but I've been using those bars mean cardinality or size of the set, and v is the set of vertices. So that means the same thing. It's just the natural log of the number of vertices. So I want the average degree to be clearly greater than that. So with 100 edges, we do the math. There's the log from there. We need about 230 edges to reach this boundary. So I'm going to set it to 250, so we're clearly over the boundary. So let's run that with, actually this is wrong. I think I was doing some edits and changed to the wrong thing. Okay, always check your code. And at one point I had 300, but I'm going to make this 250. Okay. And now we're going to graph it. This is the connected regime. We expect the graph to be connected, or possibly there's only one vertex that's missed. Well, there's 2. Wow, that's a little unusual, but you see it's taking over the whole thing. Okay. So now I would like to start looking at some of the properties of these random graphs. First, we'll take a quick look at the number of components and the size of the components in each of these graphs. Decompose, which used to have a longer name in earlier versions, will take a graph and return a vector of graphs of separate graphs, one for each component. Apply will apply a function to a vector. So we're going to apply the vertex count function to this vector or list of graphs, and we're going to make a table out of it. So that gives us, for the first graph here, it has 59 components of size 1, 13 of size 2, only 1 of size 5. So that's that. So you can see that it's doesn't really have a giant component. It's all little pieces. Now we hit the critical point where suddenly a giant component starts to appear. So we have 1 of size 24 and all the other ones are smaller. Now we're in the supercritical, where we're going to have one giant component clearly dominating the graph, but there might be some others not connected. And indeed we have 1 of size 80 and some other ones. This is just a numerical summary of what you can actually see visually there, but I'm showing you a way to actually compute this. And finally, here's our connected regime. We have 2 vertices that aren't in there yet, and all the other ones are in the giant component. Let's look at distances. So small graphs model the small world phenomenon well. The average distance here, by the way, actually the distance from a vertex here to one over here is infinite because there's no edges, but this computation of mean distance will find the average only within each connected component. So of course there the distance is very tiny because the components are very tiny. As we start getting bigger components, the distance will go up a bit. this tree-like structure contributes largely to this rather long distance for this graph. But as it becomes more and more connected, and finally we get at one giant component, the distance starts going down again because there's many different ways you can get around the graph. So for a graph of 100, we have a mean distance of 3, which isn't terribly small, but one thing we know is that as the size of the graph grows, the distances will grow as the log of the size. So even if we get to like a million or more, this distance won't get that much bigger. Okay, so random graphs model distance well, and they're actually okay with the components too, because these are kind of expected. But transitivity is the problem with random graphs, so I'll just put these out quickly. These two are basically 0, too small. So even this here doesn't give us any transitivity because we're looking for triangles. If we go now to this graph here, we still have 0 transitivity, which is kind of surprising. But when we go to the larger graph, we start to get some significant digits, but still very small. This is very low transitivity. The probability of a triangle being completed is very low. Okay, now we're going to look at degree distributions. I'm going to make a new window. Let's see, that's too big. And here's degree distributions. Also give it 4 places to plot. And let's plot the, fixing my error here, let's plot the degree distributions of these 4 graphs. Okay, and there you go. And we can see that as the graph gets bigger, we sort of get a what you might call a normal or bell curve distribution. That is not at all like what you see in natural graphs, and which are going to look more like this, which is something we'll talk about later. We can also see the same thing in histogram format if you like histograms. So let's make another window here and do the column thing and take a look at the histograms of these things. So you can see in the histogram command here how we're giving it some color and labels. You can study this plot command to learn how to make your own. Okay, so it's basically the same data just shown in histogram format. So in summary, the random graph model does a good job of modeling the growth of giant components in graphs, and actually natural graphs tend to also follow this, where there's either supercritical or connected. And it does a good job of modeling relatively short distances, although natural graphs can have even shorter distances. But it does a terrible job of modeling transitivity, which is much, much higher in natural graphs of all kinds, and degree distributions, because natural graphs will have more of a power law degree distribution, which we'll talk about later. Okay, that concludes our examination of random graph evolution.